Welcome back everyone. This is lesson 4 in our comprehensive machine learning fundamentals course, whereby today we're going to be taking a look at unsupervised learning. If you remember in the last lesson, we took a look at supervised learning and how we would rely on labels in order to categorize the data. So unsupervised learning is essentially the opposite. We categorize the data without relying on these labels. And so we use many different techniques in order to do that, which is what we're going to take a look at in this lesson. We'll also cover some real-world use cases and application for why we'd use unsupervised learning. Okay, so just more in depth, what is unsupervised learning? Unsupervised learning tries to find structures, patterns, or groupings in data that has no explicit labels. So imagine you walk into a store, right, with thousands of different products, but there's no aisle labels to tell you what products you're going to find in each aisle, in each section. And so you just start grouping items yourself by similar shapes, uses, or perhaps brand styles, without anyone explicitly telling you that this is the cereal aisle or this is the produce section. So why does it matter? Well, unsupervised learning is more cost effective, as labeling data can be expensive or sometimes even impossible. Unsupervised methods help you to explore datasets quickly. And also for exploratory analysis, often used for exploratory analysis to form hypotheses with the data or to find relationships that weren't obvious at first. Okay, and so we use something known as clustering in order to do this, and we have different clustering methods or algorithms which we can use in order to group similar items together. And so the first one we're going to take a look at is a method known as k-means clustering, and it works in this essentially in this format. So we select the number of clusters, which is labeled as k. So we choose a number of clusters that we want to identify within our data set. The next step is that we assign points within this data, which we're going to form groups around. So we group the data points to the nearest cluster center. We update these center points, which are known as centroids, and we eventually recalculate the center of each cluster based on the assigned points. And this is what we will term finding the mean average, hence the term k-means clustering. And then we just repeat that process until we achieve something known as convergence, meaning this is the best that the algorithm can do. Don't worry if that is very vague and you're not really grasping it, as we're going to go into much more detail on each of these algorithms. So with k-means clustering, imagine you pick, so the idea is essentially that you pick how many clusters you want. Of course, we've said that this number is represented as k, so it could be k equals 3, which means we have 3 groups, or k equals 4, meaning we have 4 groups. And then the algorithm assigns each data point to the nearest cluster center, known as a centroid. We then iterate this over and over again to improve these positions. So an example, you're grouping customers by their purchasing behavior, those who buy mostly electronics and those who buy mostly clothing. So don't worry, we're going to take a look at some proper examples later on in this lesson. So another clustering method that we have is hierarchical clustering, and this essentially is likened to a family tree. Okay, and one form of hierarchical clustering which we have is known as a dendrogram, and we're going to also take a look at this later on in the lesson. So building a dendrogram, we essentially create a tree, a structure showing the relationship between the data points. We choose an approach, whether that is bottom up or top down, and then we select an optimal cut. So we determine a place to cut the tree, where to say that we have enough relationships, enough data. This is the data that we want to focus on, essentially. So the idea is to build a tree known as a dendrogram that merges the data points bottom up or splits them top down, and there's no need to pre-specify the number of clusters. And the use case why we'd use this is in terms of visualizing the data's similarity structures, deciding the best number of clusters from the tree. Another form of a clustering method we have is DB scan, otherwise known as density based scan. And we identify areas of high point density as clusters. The benefit is it can detect clusters of arbitrary shapes, meaning unstructured or uncommon types of patterns. And it's also very good for outlier detection, meaning anomaly detection. So it automatically identifies noise points, known as these anomalies, that don't belong well to any cluster, doesn't fit in well to any cluster. So the idea of the density-based approach is clusters are areas of high density separated by areas of low density. And the use case is detecting arbitrarily shaped clusters, identifying outliers, again anomalies, as points not belonging to any cluster. So some key considerations is, of course, depending on what we're trying to achieve, we would use a different algorithm, as different algorithms are going to reveal different patterns and different insights into that data. So it really very much depends on the task and what you're trying to achieve, is why we'd use these different clustering methods. And bear with me as the battery is low on my laptop, so I'm just going to plug in the charger very quickly. Right, so also feature scaling. Prevent single features from dominating, and also parameter tuning. Methods like the elbow method help choose how many groups, known as K, that we will need. Alright, and we're going to look into what all of these mean in a little bit more detail later on. So next we have something known as dimensionality reduction, and we have different methods within this as well. So dimensionality reduction, let's look at first PCA, known as principal component analysis. So the goal is to find new axes, known as principal components, that capture the most variance in the data with fewer dimensions. So an example, we want to reduce a data set of 50 features to just two or three principal components for easy visualization. The benefit is this helps to avoid the curse of dimensionality and speeds up other algorithms and can reduce noise. So don't worry if that sounded like a bunch of jargon and you didn't understand at all what that meant. We're going to go into much more detail, and I promise you by the end of this lesson you're going to understand what all of this means. But essentially what we're trying to do with dimensionality reduction is say that we have a very large and complex data set, and we need to work essentially aiming to simplify that data. Instead of having 50 features or 100 features, 100 different categories of data, we want to simplify it to just maybe 2 or 3 in the terms of principal component analysis. So with principal component analysis, or PCA, we're essentially trying to take a very large data set with many different categories, many different features, and find the similarities so that we can simplify this data into just a few categories, essentially, so that the data is more easy to interpret and also to visualize. Alright, so that's what we're trying to do in terms of dimensionality reduction. So we have other methods as well, such as TSNE and UMAP, and so these are essentially different pattern detector methods. So the idea is that you have nonlinear dimensionality reduction techniques, often used for visualization of high dimensional data like image embeddings. Okay, so when we say high dimensional data, it's similar to what I was describing before. It's data where you have many different features. There's many features or dimensions, so to speak, and we want to make that turn it into low dimension data where we don't have so many points. There's not so much complexity in the data, because when the data has too much features, too much points, it can be very hard for us to then derive any patterns or insight from it, because everything just seems as though it is one big mess. Okay. Quick pro tip: it's great for visualizing clusters in 2D or 3D, but they don't necessarily preserve global distances. It's better for exploring local neighborhood. So dimensionality reduction is essentially about making complex data with many features simplified via various grouping methods in order to visually identify patterns and interpret the data more effectively. So we're going to go into this in much more detail later on in the lesson. So here's a few use case examples for each method. So we have one scenario: a retail site wants to group shoppers by similar buying habits. So one approach, we could use k-means or hierarchical clustering on purchase frequency, average order value, and categories of interest. Say for example, we have an anomaly detection case where the scenario is that we want to spot fraudulent credit card transactions without explicit labels. So of course, one approach is clustering algorithms can of course flag data points that fall outside main clusters. Alternatively, you can use density-based methods. As a density-based method, it is very good and perfect for identifying anomalies and outliers. Recommendation systems. So we have a scenario where we want to group similar items or similar users, then recommend across these clusters. One approach is to use matrix factorization or clustering embeddings from user item interactions. Image compression or feature extraction. You have lots of image data and you want a smaller representation. So this is when of course we use dimensionality reduction, such as PCA or something known as autoencoders, which is more in the realm of deep learning territory, essentially to reduce dimensionality. Okay, so we're going to take a further look at what each of these examples mean. So let's understand the different types of clustering methods. So first, we have a terminology known as variation within clustering. And so understanding variation in k-means. So what is variation? Variation is essentially how spread out data points are within each cluster. So a simple example is like measuring how tightly packed a group of friends are standing together. Okay, and we have different types of variation. We have what is known as within cluster variation, and we have between cluster variation, measuring the different aspects of clustering quality. So I'm going to get into this further, but for an initial explanation, within cluster variation, imagine, let's use the same analogy of friends standing tightly packed together. How the variation would be how close are they standing together. So within cluster variation is how, let's say we have three different groups of friends. In group one, we could say the variation is low, as in meaning that the friends are very tightly packed together. But we might have group two where the variation is high, and so that the friends are standing all quite distant from each other, right? And so that is within cluster variation. Between cluster variation is how far the groups are in comparison to one another. Is group 1 close to group 2? So that means there'll be a low variation. Or is group 1 far away from group 2? That means there's a high variation. So you have within cluster variation and between cluster variation. How they relate. How is the variance between the different groups as a whole. Okay, but we're going to get into more detail, so don't worry if it is not yet making sense. So within cluster variation, okay, let's just focus on the definition for now. So within cluster variation measures how far each point is from its cluster center. It's the sum of the squared Euclidean distances between items and a centroid. So how far each data point is essentially from its centroid. Don't worry too much about these technical terms. Euclidean distance is just a mathematical term of figuring out how far each data point is from its group, okay, from the center of its group. So why does variation even matter in k-means clustering or averaging? So k-means aims to minimize the total intra-cluster variation by creating well-formed clusters. We want clusters to have low variation within clusters and a high variation between clusters. So in other words, we want to have a good boundary of separation between the clusters so that we know, okay, this data or this particular person belongs to this group clearly. We can clearly define this person belongs to this group because we have enough variance, enough separation between the groups. But we want a low variation within the groups. We don't want, for example, if we're trying to categorize people by height, we don't want to say have someone who's 5'5" in the same group as someone that is 6 foot, because someone that's 5'5" may be considered to be on the relatively short side, whereas 6 foot is, would be classified as tall, pretty much tall. And so we don't want these people to be in the same group. We want to have enough variation between clusters to say that, okay, this is the short people, this is the average height people, this is the tall people, So we want to have those boundaries, but within cluster, we don't want to have that massive variation to say that, oh, we have tall people and short people within the same group. I hope that's making sense. So between cluster variation, as I mentioned, is measures how far apart the different groups, the different cluster centers are from each other and the overall center. So good clustering is when we have created distinct and well separated groups. Okay, and so this is when we're going to get into an example which is going to really clarify things up for you. So good clustering, we're going to be clustering students by height using k-means averaging. So good clustering is when we want short kids grouped together and the tall kids grouped together with a low variation in each group. So let's say, for example, we've got kids that are aimed 4'5", 4'7", 4'9", 5 foot, 5'2", 5'5", 5'7", 5'9". Okay, I don't even know if I can remember all of those, but we started from, let's say, 4'5". So we want to group all the short kids together. Okay, so we'll just take a random data point. This is how k-means works. It just takes a random data point within those a random cluster center, within those data points. So it might pick, let's say, 5 foot, okay, and then we might have another cluster center at 5'3", okay. And so these will be our two cluster centers, and so we're going to decide with all these data points that we have, all these students, which group should we put them in. Okay, so we had the 4'5" person, okay, they're going to go in the 5 foot group. We have someone that was 4'7", they're also going to go in the 5 foot group. We have someone that is 4'9", they're also going to go in the 5 foot group. We have someone that is 5'1", so they're going to go in the 5'3" group. We have someone that is bang on 5'3", they're going to go in the 5'3" group. We have someone that is 5'5", they're going to go in the 5'3" group. And we have someone that is 5'7", they're going to go in the 5'3" group. Okay, and so now what k-means averaging aims to do is to repeat the process. So we're going to look, okay, and see, alright, is the amount of groups that we have correct? And we're going to aim to, we'll use a method known as the elbow method to determine how many groups that we should initially have, but we're not going to get too much into that at the moment. So let's just say we've got these two groups and we're going to repeat the process to ensure that the groups are more balanced, essentially. So we might determine, okay, that's not too bad in terms of having our cluster center at 5 foot and 5'3", but we might say, okay, let's say we want to, it's better if we have 3 groups because the variation between the groups is not so great and we have too much variance. We've got someone that is, quite a lot shorter, being 4'5", in the same group as someone who is 5 foot, and we have someone that is, let's say, 5'3" in the same group as 5'7", or what if the person is 5'9"? They're still going to fall into the same group of 5'3". Even if the person is 6 foot, they're still going to fall into this group of being 5'3", for example. And so in that case, we would repeat the process, realizing that we need to have, firstly, more groups, and does the centroid of the group, does the central cluster need to change? So then we'll repeat it again. So let's say, let's say the height goes up to 5'9", would be the tallest person in the group, and 4'5" as the shortest. So we'd repeat the process, and let's say, okay, now we have a cluster center of 5'7". We have another cluster center of 5'3", and we have another cluster center of 4'8". So the 4'5", okay, they're going to the 4'8" cluster. Someone that's 4'7", they fit very well in the 4'8" cluster. This person who is, let's say, 5 foot, they would fall. Where do they fall? I believe they fall into the 5'3" cluster. Yeah, they'll fall into the 5'3" cluster, or 4'8", depending on which one. And so you essentially repeat the process so that we have a more balanced cluster with less variation within the groups. I hope that makes sense, okay? And so bad clustering is when you have a random mix of short and tall people within each group. This would mean you have a high variation within the groups. And so the process, K-means, would naturally separate students by similar heights. That's what we're aiming to do. So in more detail, how K-means works in practice. So first is to initialize. So we initially place initial cluster centers, randomly amongst the data points, as I just gave in that height example. And so we group points to their nearest cluster. For example, we have a cluster of 5'7", we have another cluster at 6'0", etc., etc. And so we start grouping the students according to their height in which category they best fall into. Alright, and then after we've done that, we update our cluster. We review our cluster and see, okay, how can we ensure that this data is more organized and that we have the least variance within groups and a good level of variance between groups. So you move cluster centers in order to minimize the spread within each cluster, as we done previously. And this is also where mean average comes in. So as we said before, we want to find the best way to determine what the initial cluster center should be. As we've randomly selected a center point, and then we started sorting the data. So we might initially have the center point at 4'5", and the other center point at 5'8", and so there's going to be a high number of variance within groups, as someone that is 5'1" or 5'2", they're still going to find themselves in a 4'5" group. So, but you might say that someone that's 5'2" is quite tall in comparison to someone that is 4'5", and so the variance is simply too high. And so this is why we update our clusters with each iteration, meaning that we repeat the process, and we use k-means averaging in order to determine a better cluster center. So k-means averaging is where we use mean average, and so we will take all of the data points within each cluster. So say for example we had 3 people in one cluster, we had 5'7", 5'8", 5'9", in a cluster where the center was previously 5'7". So everyone in this scenario, they are falling into the 5'7" cluster. But as we're looking at the data, we've got 3 people in this group, 5'7", 5'8", 5'9". And so using mean averaging, we add up all the numbers together, and we divide by the number of data points. So 5'7", 5'8", and 5'9". The middle one becomes 5'8". That becomes the average height of all the people within that group. So our new center becomes 5'8". And so when we repeat the process, we'll find that the result being that some students might end up falling into different groups, especially if we have a very high variance within groups initially. Then when we move the center point, of course, people that were previously falling into 4'5", now if the center point is 5'0", people are going to start falling into different categories. I hope that makes sense. And so you just keep adjusting until the total messiness, so to speak, is as small as possible. So I provided for you a little analogy here. So K-means is essentially like a neat freak organizing socks, and it wants to make the neatest possible groups where each pile contains similar items. And so again, just to break down what we do is we randomly assign, we have a random assignment of points to each cluster, data points to each cluster, and this is the initial grouping. And then we iteratively improve, we continuously adjust in order to reduce the variance. And then we are aiming to achieve something known as convergence. So convergence is when the algorithm stops, when variation can't be reduced any further. So it repeats the whole process several times and then picks the best iteration, finding the best algorithm essentially. So we're just looking for the optimal grouping, so the best possible arrangement for the chosen number of clusters. But wait a minute, there's something that we haven't covered, and that is how many groups should we have initially? How do we know how many groups is the ideal number of groups that we should have? Because we could just have, in the beginning, we just had grouping people in terms of their height, whether they are short or whether they are tall. But what if some people are somewhat medium height and they don't fit well into short or tall? And so this is where we introduce something known as an elbow plot. So what is an elbow plot? An elbow plot helps to find the optimal number of K, otherwise known as clusters, by showing where additional groups stop providing significant benefits. Okay, so imagine we have a scenario whereby we own a shopping center, right? And we need to employ a certain number of security guards, but we don't want to spend additional money by having too much security guards where it's not necessary, but we also don't want to have too little security guards where they can't cover the whole shopping center in an efficient way. And so the elbow plot is essentially a method to show where the more security guards that we have, it is no longer providing enough of a benefit for us to employ someone else. So I'll give you an example. So if you have one security guard, and let's say we have 100 incidences, 100 customer complaints, then of course we need to hire some more security guards. So we compare that with having 2 security guards. Okay, we can see that the complaints have significantly gone down to 45 complaints from 100. Okay, and so we will test out, let's see, what if we hire 3 security guards? Okay, the complaints have gone down from 45 to 25 complaints. So from one security guard, to 3 security guards, we have reduced the number of incidences or complaints by 75%. So definitely 3 guards is definitely better than 1, and it's definitely better than 2. But what about if we now have a 4th security guard? Okay, the complaints has gone down from 25 to 15. It's still quite significant. That's another 10% reduction. What if we now hire a 5th security guard? Okay, we've only gone down 2% in terms of our incidences. And what if we again hire a 6th security guard? Okay, now there's barely any difference at all. So we can see 4 seems to be the sort of optimal number of security guards to hire in relation to how many complaints that we're getting in. So it's all to do with the amount of benefit. Does adding an additional group, if we were to look at again our height example, does adding an additional group help to better sort and create a category for those anomalies, those people who are somewhat in the middle, where they're not short and they're not tall? Does having another group in this instance ensure that we're going to get better separated groups where people more fit into each group in a more optimal fashion with less variance, or not? And so it's called an elbow plot because essentially because of the shape. So when you can see, okay, it's quite steep, and when it begins to sort of elbow off, so it forms the elbow shape. So at the point of the elbow, and where the data then begins to become flat, and when the data there's no longer a benefit to adding in another grouping, then this is the optimal number of what we would call K. So we can see that the elbow essentially forms or appears at 4 guards. So this is the point where adding more provides very minimal benefit. So in clustering, this shows when to stop adding groups. Okay? And so that is the elbow method of how we can use to find the number of K. So again, the elbow method reveals the optimal number of K clusters by showing where additional groups stop, providing significant value. Before the elbow, so each new cluster dramatically reduces variation. At the elbow, this is a perfect balance point. Optimal number has been found. After the elbow, there is diminishing returns from additional clusters. So like the security guard example, adding resources provides massive benefits initially. At the elbow point, you've reached maximum efficiency. So beyond that point, additional clusters create artificial divisions with minimal analytical value. Perfect. And so here's a further look at the second cluster which we earlier discussed, which is hierarchical clustering. And so it's essentially like building a family tree. So let's say we want to sort the data of different dogs that we have. Alright? And so the benefit of having a hierarchical tree is that we can see the relationships between each one. So step 1 could be it's usually finding the most similar pair. So you might say, okay, Labrador and Golden Retriever. These are the two most similar pairs that we have with the dogs that were given, the data that were given. Okay, so we pair Labrador and Golden Retriever together first. Then you find the next similar pair. Okay, German Shepherds. Okay, we're going to pair this with big dog group. Step 3, we continue building. So we have Chihuahua and Poodle, and these can form a small dog group. Step 4, we have the final connection. Okay, small dog group can relate to the big dog group due to the fact that there's a direct contrast, like light and dark. But let's give a better example. So let's say I have 8 kids. I have Emma, Henry, Frank, Grace, Anna, Bob, Kathy, and Dave. So category 1 is finding the similarity between all these groupings. And the similarity is that they're all my kids, right? And I could break them down into saying, okay, I have entertainers and I have musicians in terms of my kids. So the entertainers, I've got 3 entertainers, sorry. So I've got Emma and Henry. No, I do have, sorry, this is a bit, yeah, so I've got, is there 7 or 8 kids? Hold on. We've got Emma, 1, 2, 3, 4, 5, 6, 7, 8. Right, I just think that the formatting is not that great, so please forgive me. So Frank and Grace, they should belong to the comedy section. Alright, so the similarity is that they're all my kids. The second category is that we've broken them down into entertainers and musicians. So Emma and Henry, they belong to the magic group. And the comedy group, we have Frank and Grace. Again, forgive the poor formatting, I'm not sure what's happened there. Okay? And so category 3, we can further break down the entertainers into magicians and comedians. So the most similar would be Emma and Henry. Even though Emma, Henry, Frank and Grace, they're all entertainers, and all of these, Emma, Henry, Frank, Grace, Anna, Bob, Kathy, Dave, they're all my kids. We are breaking them down in terms of their similarities, in terms of the data that we have been given. So this is the benefit of the hierarchical structure or the dendrogram tree. And the dendrogram tree, it helps to easily identify relational connections. Okay? So if we to compare the two clustering methods, hierarchical versus k-means, these are the key differences. So k-means, it's like having a restaurant seating plan. Hierarchical, it can be more likened to a family tree. Within k-means averaging, we must decide the number of groups first. With hierarchical, we don't need to decide a number up front. We can have as many, we can keep going until we essentially establish depending on what goal or what task we're trying to accomplish, what insight are we trying to get from this data. With k-means, we seek to have everyone precisely in one table or one group. Hierarchical is just showing the relationships between the different groups. With k-means, we don't visualize any connection between the groups, but with hierarchical, we can cut the tree at any level, and there is relationships between the groups. Alright, so our third and final method for clustering is something known as DB scan, otherwise known as density based scanning. And so we have an example of, we want to group people at a concert, and we want to find the natural crowds that are occurring at this concert. So we've got some people, group 1, near the stage, so you see a dense group near the stage, and we're going to call that group 1. We also see a very big group, a very dense group at the food truck, and so we're going to call that group 2. We also see a very dense group at the merchandise stand, and so we're going to label that as group 3. But then there's also some scattered individuals where they're not a massive group, or people walking alone, or people just in pairs. Okay, so there's not a dense base groups, and so these are more scattered individuals, and they don't belong to any group. Okay, so how does density based scan work? So first we pick a person and we count the neighbors within arm's reach. So let's say, for example, we're going to categorize people in terms of 5. So 5 plus people, if you have 5 people within a group standing nearby, we'll say, okay, this will be group 1. We'll label this as a crowd. But if there are fewer than 5, then okay, we're going to keep looking because they're too scattered, so we don't call that a crowd. The next step would be to essentially grow the crowd. So we add all the neighbors onto that crowd. All the people that are in arm's length, okay, they can add to that crowd. We can add that to the crowd. And so we check their neighbors too, and we keep growing until there's no more connections of these groups of people to be added to this crowd. And so we repeat the process, finding the next natural crowd, and we keep going until everyone is checked. And so some people will remain unassigned. So this is the big difference between density-based scan, for example, as in comparison to k-means clustering. With k-means clustering, everyone will belong to a group. It will find their most similar group. But with density-based scan, it's much more natural, and some people just don't fit into any group, and we're completely fine with that, and so they will be classified as the outliers or the anomalies. So let's give another example of, we're at a coffee shop and we want to group people within a coffee shop using this density-based scanning approach. So with the DB scan approach, we're going to find natural groups and we're going to leave the loners alone. Alright, within the hierarchical approach, we're going to connect everyone using some kind of big family tree, finding the relational elements between each person, and forming a tree of connection in that way. With the k-mean approach, we're going to create different groups, and everyone is going to end up in one group or another. Okay, so it forces everyone into predetermined groups depending on which group are you best fit for. Okay, but with the density-based scan approach, in a coffee shop with, let's say, 50 customers, DB scan would naturally identify the study group of, say, 6 students studying together, and perhaps a business meeting of 4 people, while recognizing that perhaps 8 people are reading alone, and so they don't form a cluster, and we're completely fine with that. So here's a comparison of each of the different methods, so a visual comparison. So cluster 1, we're trying to form neat groups with as least variance as possible, with everyone being forced into a group. Hierarchical is that we just show how each group sort of relates and everyone is connected in some kind of big relationship tree. Where density-based scan is the most arbitrary of all of them, where the clusters aren't any particular shape or size. It's just we're grouping people depending on natural crowds that is forming, natural patterns that are forming, that are close together, and isolated points are left alone. So if the data is too random, it doesn't make sense. It's not we're not forcing any data point into any category. Essentially, this is where we'd use density-based scan. So comparing further the three clustering approaches, so k-means forces everything into neat circles, neat clusters, neat groups, and requires knowing the number of clusters in advance. Hierarchical, it connects everything in a family tree and shows the relationship between all the points. A density-based scan categorization finds the natural blob shapes and leaves the loners alone. It doesn't need predetermined clusters, a predetermined cluster count. So when is a use case when we would even use density-based scanning? Well, we would use it in, for example, disease outbreaks. We'll find dense areas of cases of outbreaks, for example, on a map. Or we would use, for customer behavior, identify natural patterns in purchasing data. Fraud detection, spotting unusual dense patterns in transactions. Or spatial analysis, finding natural geographic groupings. So it's groupings that form naturally. So we're not trying to manipulate the data in any way. Whereas with k-means, we are somewhat manipulating the data, saying, okay, this is the best fit. With density-based scan, we're just looking to see, okay, what are the natural occurring patterns without any input from ourselves. Okay, and so choosing the right clustering method. So you can see these are essentially the different properties that each clustering method has. So k-means is the dark one here, hierarchical is the more somewhat bit lighter medium grey, and density-based scan is the light grey. And so I've given each a rating score in terms of each of its key features. So if you want flexibility, k-means, of course, it's forcing everyone into a group, so it has the least amount of flexibility. Hierarchical is a lot better because it starts to show the relationships between each one and so forth. But density-based scan is the most flexible as it's the most natural. Pardon me. In terms of speed, k-means is the best in terms of speed. Hierarchical is the worst in terms of its speed of how you can, at a glance, analyze the data. And density-based scan is somewhat in the middle. Handles noise the best. And when I say noise, this is where we're talking about outliers or anomalies. Of course, k-means is not good at this at all, as everyone is forced into a group. Hierarchical, it does it somewhat better, as you can decipher from. It preserves much more information, so you can see via the relationships where the anomalies and the outliers may lie. But density-based scan is especially made for this. It's natural, it's a way to leave the loners alone. We're not forcing anyone into a group. We'll see if there's a pattern, if there's data that is completely what we know as outlier data, anomalies in the data, then we leave those alone, and so we can clearly see it through the density-based scan approach. Interpretability, of course, hierarchical would be the best as it shows all the relational data. K-means is pretty good. Density-based scan would be the worst in this case, but it's still not terrible. And of course, irregular shapes. We know that k-means forces everyone into groups where we want low variance, so we want the groups to all be of similar shapes and sizes. So this would be the worst in terms of irregular shapes. Hierarchical is not bad. Density-based scan is the go-to. So choose density-based scan when you want to find natural groupings without forcing everything into clusters. It's ideal for discovering patterns in complex, noisy data with irregular shapes. Okay. So common pitfalls and challenges. So of course, choosing the right algorithm. As different algorithms are going to uncover different patterns, you need to first think about the task that you're trying to accomplish and choose the algorithm that best suits the task that you're trying to accomplish, essentially. Subjectivity. There's no built-in correct answer to validate against when it comes to unsupervised learning. Scalability. Some algorithms struggle with larger datasets. Overfitting. There's a risk of over-clustering or choosing too many components. In supervised learning, you can measure accuracy against known labels, whereas in unsupervised learning, there's no built-in correct answers. And so domain knowledge is often the key to making sense of these clusters or these components. So having expert knowledge to be able to properly interpret the data that you're looking at. So key takeaways from today's lesson: pattern discovery. Unsupervised learning finds hidden patterns without labels. We looked at the different clustering techniques such as k-means, hierarchical, density-based scans for grouping similar points. We also briefly looked at simplification methods such as dimensionality reduction in order to simplify the data, aiding in visualization and the feature extraction. So remember, we had, say for example, 50 features, and we want to lower that down onto 3. And the reason, I'll give you an example of a use case where we would use dimensionality reduction is, say for example, with Google image recognition. So we have something known as image embeddings, right? And image embeddings is essentially trying to map. Okay, let's say we have an image of an apple. The image of an apple with image embedding, it's storing thousands of different features as to how it identifies that image as an apple, right? So it could be the curvature of the image, it could be specific shapes and many different semantic features, many different features, details that determine that image is an apple, for example, okay? Or when you're looking at a face, there's many features that are going through our minds when we're looking at a face, determining each and every detail as to how we recognize a face. But the human mind is so amazing that it just does this, on autopilot, essentially. But when we have a machine, we're trying to teach a machine how to recognize faces. And so the image embedding is storing all that thousands of features, thousands of pieces or hundreds of pieces of information, and things can just become essentially overwhelming. So this is why we have the simplification methods in order to simplify this data. And so with things such as TS&E and UMA, it's very good for image detection with things like Google recognition, as we're essentially, what is happening is that we're taking loads of images, let's say of an apple, and we're storing all this data. We're storing all this data of an apple, and we're linking it to the word apple, so that now when we see a new image of an apple, we have these text and image pairs of an apple, and so that we're going to say, okay, I recognize this new image of an apple. It searches its database and it says, let's say I give a prompt and say, show me a picture of an apple and a pear. Or, sorry, forgive me. Let's say I give an image of an apple and I say, is this image an apple or a pear? And the model, the algorithm, will then search its database and say, okay, let me find the semantic data, the linguistic data that I have for an apple. And it pulls up all these images that it's, seen as an apple. And it will produce the image of an apple, for example, as opposed to the image of a pear. Seeing that a lot of the characteristics and data is different, but it's in terms of simplifying its complexity. So behind the hood, what is essentially happening is that the model, the algorithm, is storing every face. Let's say if I take 5 pictures of your face or 5 pictures of an apple, I'm grouping these all together, similar to the classification method. And so that is how it is taking all these features and simplifying it into one, storing all these images of an apple or storing all the images of your face in one section. So when let's say you try to unlock your phone by using your camera, it will say, okay, does this face match the images of the face that I've stored to say unlock the phone? If it is yes, by its groupings of how it has stored this semantic information, how it has stored this information of your face, then it will unlock the phone. Okay, so that is somewhat of a, it can be quite complicated to explain, but that is somewhat essentially what is happening with these different simplification methods. Okay, and practical applications. So we looked at some real world use cases such as customer segmentation, anomaly detection, and recommendation systems. And that pretty much concludes it for today's lesson. Thank you so much for Okay, so key takeaways. So in today's lesson, just to recap, we looked at pattern discovery, unsupervised learning, finding hidden patterns without labels. We looked at the different clustering techniques such as k-means, hierarchical and density-based scan, grouping similar points together. And we also looked at some simplification methods such as dimensionality reduction, PCA. So key takeaways from today's session. So of course we looked at pattern discovery. For unsupervised learning is finding hidden patterns without the labels. We looked at different clustering techniques such as k-means, hierarchical, density-based scan, and how they group similar points together. And we looked at the simplification methods, otherwise known as dimensionality reduction, such as PCA, TSNE, and UMAP, of how he simplifies the data, aiding to better visualization and feature extraction. And we looked at some real-world use cases such as customer segmentation, anomaly detection, and recommendation systems.